I'm Saumil Patel. I'm a researcher at Argonne National Laboratory, a postdoc. I've been there for about 2 years. And since I started there, I've been working on simulating engines. And I'm using a code called NEC 5000, which it's a high order code, and high order in the sense that it's spatially resolved. So we're able to look at a lot of different scales that occur in a fluid, and we're able to look at a lot of different interactions that are occurring on a turbulent level. In particular, we were interested in simulating an experiment that was done out of General Motors. The experiment was something that was important for the Department of Energy because trying to increase the efficiency of engines is an important thing for, I guess, anyone in any country. That way we're able to use our resources a lot more efficiently as a country. So in my work, we looked at simulating multiple cycles of this experimental engine done out of General Motors. And in particular, we were concerned with trying to get these simulation results so that we can facilitate the engine design process a little bit better. We were concerned with a couple of things. One thing is being able to simulate this turbulent flow field that occurs inside an engine, inside a very complex geometry, inside a geometry that's moving. As you know, you have pistons, you have valves, you have these boundaries that are moving, and not necessarily in a fashion that is obvious, let's say, but in a fashion that is known a priori, which kind of helps facilitate the simulation process a little bit better. Anyway, we were able to put together some capabilities where we could get these cycles in less than half a day. And this is a factor of 3 speed up over standard methods. And we were able to get 30 cycles of what's called the gas exchange process, where essentially you're intaking air, compressing it, expanding it, and then pushing out the exhaust. So we're not doing combustion right now, but the reason this particular setup was important was because we want to be able to see what kind of turbulence happens at the end of the compression step. So at the end of the compression step is when combustion occurs. So it's not too clear what kind of turbulence is going on. And the reason turbulence is important is because it burns the gas a lot, or burns the fuel-air mixture a lot efficiently. So the more turbulence there is, the better burn there is, and the more efficient your vehicle engine is. So this was a proof of concept work just to make sure our capabilities and our, let's say, the technical aspects of our simulation were running well. And we gained some confidence in getting some of these cycles, and we hope to do more in the future.